mixed hydrogen peroxide.
Yes.
What percentage?
30%.
Can I bring up safety as a point?
Sure. Yep.
Goggles?
No.
Protect those eyes.
It's pretty strong stuff.
Yeah, completely.
Yeah, absolutely. Okay. Yeah, as a high school teacher, yeah, definitely would have them have especially in demonstration. Let's see, what else? Let's see. How about test some knowledge? Can you give me the approximate wavelength of the colors you have there?
Blue is going to
in nanometers.
Okay, lucigenin, if we start with blue, it's going to be somewhere from like 450 up to about 500. And then yellow is going to be yellow's going to come after green, so yellow is going to be somewhere around about 550, 560. And then red at the top is going to be anywhere from like 670, I'd imagine about 700 nanometers, because the spectrum, visible light is 400 nanometers, 700 nanometers, so. Those are rough estimates. They vary, but that was, yeah.
Excellent. Round of applause back.
Of course he knows. Yeah, he knows it. He knows it.
I was curious, this seems sort of like how a glue stick works?
Yes, as the glow stick, it is a similar process to how a glow stick works, except I believe that the energy used in that is actually stored and then emitted. So that is probably a different form of luminescence, because lucigenin lasts roughly, when refrigerated, for I would say about anywhere from 5 to 10 minutes. As we cool it down, it slows the reaction down. Glow sticks, as we know, can last a lot longer than that. That is a way I would imagine the energy that is then created through a chemical reaction as you snap the glow stick, that becomes stored and is slowly emitted over time. So it does have similar properties, as in it is a form of chemiluminescence, but it lasts longer, so it's not exactly what we have here.
I guess my question is, I can see, especially here on the right, you have one source of light, and the same thing's happening here. So you basically have some bluish, purplish photon. But you have something that's emitting different colors. And so why am I seeing something absorb the same color of light, but emit different colors of light?
Well, as you know, if we took the black light away and just left let's take it away here, the colors don't actually fluoresce as much, because we have a lot more light in the room, different like interference and stuff. But as we, the UV light here, the UV radiation is that is being absorbed. Each one has its own. This is naturally it's a red fluorescent disol. This one's like a yellowish green, and just the focusing of just one energy source providing energy is enough to just solely excite to fluoresce each dye on its own. It has to do with the fluorescent dye being used. The rhodamine naturally is a reddish when it fluoresces. The fluorescein is more yellow-greenish, and lucigenin starts out bluish-green, then it's going to be bluish-green here because we just have fluorescence, but then in the form of chemiluminescence it goes to blue. So.
And then, so I guess I have at least one other question.
Yes.
Since you're on a roll here. So if it's not emitting light,
Yes.
right? So you have this formula up here.
Yes.
And so I'm guessing then that the one that's emitting red is emitting a photon that has a little less energy.
Yes.
Right?
Because that.
Right. No. But you started with blue, which is because it's more.
The high thing.
What's happening to the energy that isn't emitted?
You're asking that we have red, yellow, and blue. What happened? Like, why does this one absorb energy? And then, well, as the electron returns to ground state,
Right.
during that relaxation period, and it emits that photon, some of the energy actually is given off to other parts of the reaction itself. As we saw with the lucigenin, as that blue photon returned to ground state, some of its energy was actually given off to the original unused lucigenin, which in its turn excited. So as the energy that's absorbed, that's absorbed and excites those electrons, as that electron returns to ground state, it's going to have slightly less energy, because parts of it is going to be given off to different parts of the solution as we have here.
This is a really cool reaction. I haven't seen this one before. Do you try any other dyes besides fluorescein and rhodamine?
We did not, but like I said here, I would imagine we probably couldn't use blue. We probably couldn't use another blue dye, because as I just stated to him, the energy as it's relaxing would probably not. I don't know specifically, but would probably not have enough energy it would not give off enough energy to be absorbed by another blue dye, but red, orange, yellow, green, all of them, if we use those dyes, should all fluoresce because they have higher wavelengths and therefore will require less energy to fluoresce.
I think you did a really great job. I mean, you know a lot about this reaction, and your information was really great. So I really appreciate it.
Is there a threshold, that you said it goes from shorter wavelengths, more energy, to longer wavelengths, less energy?
Yes.
And you have to, it has to go in that direction. Is there a threshold of how close together that you know of that you can get these things, or was it?
Like how close, so you're saying like the blue photon, how close I could get it? How almost I could measure the energy and see how close colors I could get to that energy I could actually use?
Yeah.
I mean, I would probably have to, I would say, chemically determine the wavelength given off, and then plug it into this formula, determine the energy, and then get the energy of a very close color, maybe a blue itself. Probably not a violet, probably takes too much energy, but I'd probably just have to, like I said, measure the wavelength of the blue photon and compare it to how much energy is required from the wave, after plugging the wavelength of what I want to possibly use the blue photon to provide energy for. So I would most likely have to measure that experimentally, but